Okay, we have seen in the previous video that when a charge is moving in a magnetic field, then the charge always experience a magnetic force. So when I say magnetic force, it means the charge, it will deflect. Okay, instead of going straight, so because of the presence of the force, maybe right, the charge will not go straight, but it may deflect either left or right, depending upon the directions of motions of the charge. Okay. We have also seen, right, before that when the charge is moving parallel to the magnetic field, then the charge will have zero magnetic force. Okay, so but in this video, we will consider another case, that is when the charge is moving perpendicular to the magnetic field. Okay, so here I have written motion of a charge in a magnetic field when the initial velocity is perpendicular to the field. Okay, so first I will explain to you, right, how do we represent the magnetic field which is perpendicular to the plane. Like if my magnetic field, right, are acting perpendicular to the plane, so for that we represent by a cross. So this cross here means the magnetic field it is perpendicular to the plane of the board. Okay. Now, if I have a charge plus q, and this charge plus q, because see, look here, I have this is the magnetic field, and if the charge is entering the field, let's say initially in this way, perpendicular to the field. So this velocity v, which is actually the velocity of the charge, right? It is perpendicular to the magnetic field. So if you apply Fleming left hand rule, this charge will experience a magnetic force, in this direction. Look, this is the magnetic field, which is represented by the forefinger. This is the directions of motions of the charge, and this is the directions of the magnetic force. So at this point, right, the charge will be deflected this way. So if the charge is, moving ahead, then because of this deflection, then the charge now, instead of going straight, now it will turn around. Okay, now at this point again it will experience a magnetic force acting in this way. Similarly, at this point it will experience a force this way. When the charge has come here, it experiences a force this way. At this point, at this point, at this point. So if you join all these points of the part where the charge is moving, then you'll get like a circle. So now this circle here, let's say it is having a center O, and the radius of this circle, okay, I'll drop all these, now you have understood. Suppose the radius of the circle in this case, let's say it is R. So please remember that a charge moving perpendicular to the magnetic field, right, will experience a magnetic force towards the center of the circle as shown here. Okay, all right. So what happened is, because the charge now it is uh, deflecting, or it is moving, in a circular path. So therefore, at the same time, the force which is experienced by the charge, it is acting towards the center. So it means here that the charge will experience, a centripetal force. Okay, I hope you still remember in class 11 when we talk about centripetal force. It is a force which is directed towards the center of the circle. Okay. Now, who provides this centripetal force? From where does this centripetal force comes? This centripetal force, it is nothing but it is the magnetic force only. It is the magnetic force. So centripetal force, right? It comes here because of the magnetic force. Because the magnetic force, it is F. So this F, it is acting towards the center. So therefore it behaves like a centripetal force only. Okay. Now another point that you need to note down here is, as the charge is moving perpendicular to the magnetic field, please remember that the work done on the charge is equals to 0. When the work done on the charge is equals to 0, it means that the kinetic energy of this charge, okay, does not change. Or I can say that this charge here, it is moving with a uniform speed. So why this work done is equals to 0? Work done is equals to 0 because, as you know from the definition, work is equals to F dot S, force into displacement. And F dot S means Fs cos theta. What is theta? Theta is the angle between the force and the displacement. See, at this point, the force is acting perpendicular to the boat, and the displacement at this point, it is along the directions of velocity. So it means theta is 90 degree. So when theta is 90 degree, so this will become Fs cos 90. But you know cos 90 is 0, so therefore 0 into Fs will be 0. So this work done, which is equals to Fs, now it is equals to 0. So when the work done is 0, as I have already mentioned before, the kinetic energy of the charge will not change, because actually kinetic energy, right? This work, if you remember in the work energy theorem, the net work done acting on a particle, it is actually equals to the change in kinetic energy. But since the work done here is equals to 0, it means there is no change in kinetic energy. So for kinetic energy, we know the expressions is half mv square. So when this does not change, it means the velocity is constant. So therefore, when a charge is moving initially at a perpendicular directions to the magnetic field, then this charge will be moving with a constant velocity. Okay, so let's come back here. I have, told you that this centripetal force is equals to magnetic force. How? This centripetal force, I will write, because you know from the expression mv square upon r, which is the expressions for the centripetal force. And for the magnetic force, we know it is qvb sine theta. But theta, it is the angle between v and b, so here it is 90 degree. So I will get mv square upon r is equals to qvb sine 90 is 1. Okay, so this square of v and this v cancel. So you will get here, if you find out r, I'll take first the reciprocal r upon m. This will becomes 1 upon qb. So just r will be equals to m upon, I think I miss out this factor mv here. Okay, so just r will be mv upon qb. So this is the radius of the circular part, which is performed by the charge in a uniform magnetic field. Okay, now I'll name this as equation 1. Okay, after this, let us look at the time period of revolution. Okay, we know time period t. Time can be written as distance upon uh, velocity. Yes or no? Because we know time is equals to distance upon velocity. But when I say distance here, it means the distance, because time period, it is actually the time taken to complete one revolution. So for one revolution like this, what is the distance which is moved by the charge? That distance is equals to the circumference. So instead of distance, I will write circumference. Or t is equals to, we know circumference is equals to 2 pi r, and this velocity, it is v. Okay, or here t is equals to 2 pi r, I'll write it this V. Instead of R, I'll substitute mv upon qb. So this V with this V cancel. So I will get T is equals to 2 pi m upon qb. So this is the time period of revolution of the charge. Okay, this is my equation 2. Now from this equation 2, we see that the right hand side, okay, it is a constant quantity because 2 pi is a number, m, mass of the charge, okay, that is also a constant which is unknown to you. Charge of this particle also is constant. Even the magnetic field which you are applying perpendicular to the board, this is also known quantities. So therefore all quantities involved on the right hand side of this equation 2, they are constant. So therefore this time period here, it is constant. So time period is constant. It means that, right, whether the charge it is small or big, that charge will always take same time to complete the circle. Okay, which means if I have two circles here, small circle and big circle. For the small circle, right, let's say the time taken to complete one revolution, let's say it is 1 second. Similarly, if a charge is, performing this circular part in a larger circle, then again the time taken to complete one revolution will be 1 second. Why? Because time, right, it is independent of the radius and the velocity. We don't have radius, we don't have velocity here. So time is independent of the radius and the velocity. But the thing is, how come this time period in a smaller circle and a bigger circle is the same? Right? Right? How this is possible? This can be possible only if the charge, when it is in a smaller circle, it should be moving with a small velocity, or inside or in this small circle the charge is moving slowly, so the time is 1 second. But in a larger circle, right, it is clearly that the distance is large. But if the distance is large, if the velocity of the charge it is the same like in this circle, then the time would be more. But in order to get back 1 second, then in this larger circle the velocity should be more. It means the charge here should be moving faster, and here it is moving slow. Okay. So this is all about the motion of a charge in a magnetic field when the initial velocity is perpendicular to the magnetic field. And in the next video we shall see about another case when the charge is moving at some angle with respect to the field initially.